Rocket is nothing, but we can simply define it as a carrier vehicle that helps us to put something, that something may be cargo, crew, experiments, that is payload, at the required orbit, that is the destination. Now, another question for you all is, do you guys understand what is the basic difference between a rocket and a missile? Okay, so basic difference between a missile and a rocket is that the payload. Basically, missile itself is a rocket. It has everything that a rocket has. But the critical change that comes between a missile and a rocket is the payload system that it carries. For a rocket, as I mentioned earlier, the payload can be cargo, crew, and various experiments or instruments also. But for a missile, the payload is explosives, right? So and also missiles sometimes what they have is they have wings or canard systems. So like an aeroplane, as we have wings on an aeroplane, sometimes we have wings which are attached forward to the body tube, which are known as the canards. So missiles might sometimes have wings or canards, but rocket usually do not have wings or canards. So when I think, or when we in general think of designing a rocket, the very first thing that comes to our mind is the mission purpose. That is, what are we designing this particular rocket for? Are we going to design it for cargo delivery? Are we going to design it for conducting experiments in microgravity? Or are we, using it to put our astronauts into certain orbit, as in to put astronauts in ISS, right? Then second thing that comes into consideration is mission requirement. That is, at which particular orbit or altitude we want it to reach at the maximum point and deploy our payload. Then we also decide if it is a crewed uh, launch, then we take into consideration the weight of the crew members. And if it is not, we take into consideration the weight of the payload or the instrument or whatever it is going to deliver. So combining the weight of the crew and the weight of the payload, we get the total weight that we are supposed to carry in a rocket. Now once we have the weight that we want to carry to a particular altitude or a particular orbit, we now start thinking about the propulsion system that we'll be using, because that will give us an idea about what or how much fuel we are supposed to carry with us, so that the rocket reaches that particular orbit and delivers the experiment or cargo or crew. So once we have all these things with us, then we start designing it on various softwares, then we do analysis, then we do the prototyping, and then finally we launch and we do the post-launch examination. Now, what comes in the post-launch examination is the examination of the fuel and the motor that is being used, and also of the external structure of the body. Talking about the external structures or components of a rocket, as you can see here, on the open rocket screen, there is a box on the right side which says add new component, and there are a number of components. Now we'll go through each one of them and try to understand the basic purpose. Okay, so first comes is the nose cone. Now nose cone, you all must know, is the very first part of the rocket body that comes into contact with the airflow. So what it is doing is trying to provide less contact area, so that there is less friction between the rocket body and the air that is flowing, right? So that is, it is trying to minimize the friction. In turn, it is trying to minimize the drag. Now you all must be aware of the aerodynamic forces that act on a rocket, which are lift, drag, weight, and thrust. So in order to overcome drag, we have we minimize the area of the nose. So that is one of the purpose. Then there are a number of shapes of nose cones that have been used, like the conic, then there is blunt conic, there is double conic, there is elliptical as well as parabolic. But the very common that we use for our competition, or even for general purpose for model rocketry or experimental rocketry, is the ogive cone. It is used because it is the most common, easy to manufacture, and you can it is cost effective, as well as students are making this particular rocket. So mostly commonly used nose cone in the model rocketry is the ogive cone. Now then second is the body tube. Body tube, as in everything starting from the leaving the nose cone, starting from there till the fins, that everything comes into the body tube. Now body tube mainly hosts the combustion chamber or our motor, and second is the guidance system, guidance and navigation system if we are using one. Then body tube also has fins attached to it. So basically, why we use fin is the very straight logical answer is to provide stability to our rocket. Because what fins does is, suppose there are wind gusts coming towards your rocket and we have three fins. Now, when air generates pressure on one of the fin, it will try to rotate it into one direction, right? Similarly, the other two fins will do the same thing. So what is happening? The fins are helping the rocket to swirl, which is to move in a straight line, disrespect of the wind flow, the heavy wind flow. So in very generic form, the fins provide stability to the rocket and help it move straight upwards. Sometimes you must have observed that in the launch vehicles used by ISRO, there are no fins. So what is exactly used when there are no fins? Sometimes we use a system called as the gimbaled nozzles, wherein we do not have fins to give stability or guidance to our rocket. In place of the fin, we use the gimbaled nozzle, as in the nozzles which can move freely at certain angles, and they can give direction and stability to the rocket. If there is absence of fins, we are using gimbal nozzle systems. Now, talking about fins, there are a number of shapes as well. So there are square shaped, rectangular, elliptical, straight tapered, and then swept tapered. In swept also, you have forward swept and backward swept. But if you're just talking about the shape of the fin, then the most efficient is the elliptical one. Why? Because you must have, if you have not, tried to get an idea over lift and the induced drag. So what happens is, consider a fin structure. The very small tip of the fin that is there, air flows over it. Now that gives certain pressure and it generates small amount of lift. But due to the generation of small amount of lift, we also experience a small amount of drag, which adds to our total drag. Now this induced small drag is called as the induced drag. Now we want to reduce that drag because we do not want our vehicle to slow down, right? So the tip of the fin plays a very major role, because when we talk about wings, we talk about airfoil, right? Similarly, when we talk about fins, we also talk about airfoil. The more uh, you know effective airfoil you have, the more effective your fins will be. So in generic way, if we just talk about the shapes, elliptical are the most efficient. But when we actually come to practicing the model rocketry or building the rockets, the mostly commonly used are tapered wings or the rectangular wings because of the airfoil. You can check out why the airfoil is plays an important role in the fin structure. That will be your homework and will also help you for a better understanding of stability of the rocket. Now, talking about the stability of the rocket, there are two important things when we talk about the stability of the rocket. The very first is the center of pressure, and the second is the center of gravity. Now, to define what is center of pressure and center of gravity, so center of pressure is nothing but the pressure exerted by all the aerodynamic forces act at a single point on the rocket body, right? So that single point is called as the center of pressure. And center of gravity, it is the point where the force of gravity acts on the rocket body. So if the ideal condition for stability of the rocket is that the center of pressure should be behind the center of gravity. Now, what happens is, the formula to calculate the static margin, the word used is static margin, which gives you the distance between the center of pressure and center of gravity, is 2 into the diameter of the body tube. Now ideally you don't actually use this 2 into diameter of the body tube. The range for stability of model rocket goes around 1.88 to 2. It's calibrated around 1.88 to 2, and it's considered to be more than efficient for model rocketry. Okay, but now how we manage or how we move a center of our center of gravity or our center of pressure. If you take a pencil and you try to balance it on your finger, the point where the pencil gets balanced on your finger, that point will be called as center of gravity. Similarly, there is no technique that will help you to determine the center of pressure. So we use model rocketry softwares like open rocket, which help us to give the idea about how stable our rocket system is built. So if you want to move back or ahead your center of pressure, you use fins, because fins are again directly related to the stability of the rocket, right? So to manage center of pressure, we either increase or decrease the fins. And also sometimes, as I mentioned earlier, missiles have wings and canards that too affect the center of pressure. But center of gravity, it is affected by the mass content. So either by reducing or increasing the mass, you can move your center of gravity or center of pressure. So that is how we deal with the stability of the rocket. Now we have covered nose cone, body tube, fins, types of types of nose cones and types of fins. The most efficient practically to be used is, rectangular or tapered. And just talking about shapes, it is elliptical. And in case of nose, the efficient, which is used commonly throughout in model rocketry, is the ogive shape. Now coming, there is one last component in the body components and fin sets, that is the launch lug. Now, if you have observed launches which are done by ISRO or many other space agencies, you will see that there are big metal barricades that hold the entire launch vehicle, right, to make it stand straight, right? But when we are performing model rocketry, we do not have such a huge setup. What we have is a small, um, just a second. What we have is a small launch pad that is nothing but a metal rod with a small platform, which helps us to keep our rocket straight. So to arrange our or put our rocket into the rod, we use the launch lug. But the disadvantage of launch lug is that, as I earlier mentioned, if you increase the unnecessary area, you're unnecessarily increasing the drag, which is indirectly going to affect the speed of the model rocket. So when you are putting launch lug, you are increasing the area. And that is again producing some kind of drag, which is acting to the total drag and again slowing a rocket down. So when you are putting launch lugs on your body tube, make sure they are not very big and not very thick. They have the optimum and smaller in size. The smaller they are, like, they should be stronger, but they should not be very large, of larger area, because then again that contributes the drag. Now, in the inner components, we have inner tube. Inner tube, as in, if you watch videos, just go and watch, because that will really help you to visualize things. When you put your motor into the combustion chamber, you have an insulation layer or a tube which is between the body tube and the motor. So you can use inner tube for that purpose, or if you want to uh, put anything extra, we can use inner tube. Then there is coupler, as in, to join my nose and body together, I will use a coupler to couple them together. But again, a disadvantage of coupler is that you are like connecting two different body surfaces, right? So when you're connecting two different body surfaces, there is some interface between them. Now, this discontinuity in the structure again leads to a drag, which is called as the interference drag, due to the interference of two bodies, which again contributes to the total drag of the body and tries to hamper the speed or the effectiveness of a rocket. So mostly try avoiding using multiple sections joined together when you're trying to build an actual rocket, and also when you're trying to model it. So it is always better to have a continuous body, so that there are less interferences and there are less drag produced due to it. Then comes center ring. Centering is something that holds everything that is inside the body tube, as in creating compartments or giving or allotting area, so that these things do not move into the next things or collapse with the instruments, right? So they use as a barrier. They are used as a barrier. Then there is bulkhead. Bulkhead is used, if you when I'll talk about the recovery system. Bulkhead is used mostly in the recovery system, where we connect the shock cord and the shrouds, the parachute and the nose cone and the body tube together. We mostly use bulkhead. Then there comes engine block. As I mentioned, that the motor that is present in the combustion chamber is heavy and has fuel which has like which generates greater pressures in psi. So sometimes what happens is, when you put your rocket on the launch pad, that is the rod, you attach it with the launch lug, you give the ignition charge, and the fuel starts burning. But the rocket stays there, and the motor itself tries to tear apart the entire rocket body and goes up into the sky. So in order to avoid the loss of motor and any damage to the body tube, we try to inculcate engine block. as in a block that will avoid the motor to tear apart the body tube and move ahead and push the nose out. Okay. Now, also another significance of using engine block is that once we do the launch, we do not want to lose our motor. We want to recover our motor as it is, because manufacturing a motor and the and doing the machinery is very expensive. So it is better that you create motors which are usable for launches. So that's the purpose of engine block, as the name suggests, to block the motor that to tear apart the body. Now comes the mass objects, where there you have, I guess, parachute, shroud lines, and mass component. So as I mentioned earlier, whenever you do a model rocketry project, you will always have to create an inbuilt recovery system, because just launching your model rocket is not the goal. Recovering all your components may be safely and soundly or sometimes damaged, but recovering them is important, because as I mentioned, the motors are expensive than the entire other components combined, and also you spend a lot of efforts in it and energy, so it is better that you recover your rocket. So for that purpose we use recovery system. Now this recovery system is made up of nothing but parachutes. Now you must have seen Perseverance landing in the Martian atmosphere using the parachute. So, what was the purpose there? It was to simply slow it down. Similar is the purpose here in model rocketry. When we use parachute as a recovery system, what we are doing is we are putting our parachute in between the, sometimes completely into the nose cone, or sometimes between the nose cone and the body tube. So what happens is the parachute is connected with the shroud lines. Shroud lines, as in the lines that run from the canopy of the parachute to the one single point. And maximum lines can be around 6 to 8. That is, those ropes can be about 6 to 8. Once we have the canopy, the ropes attached to each other, now we attach this canopy and shroud lines, or the elastic ropes, to another elastic cord, which is called as the shock cord. Now this shock cord, what it does is it holds the entire body tube, whatever is there inside the body tube, and the nose cone as well as the parachute, all three together. So that when there is ejection of the parachute, the nose cone and the body are intact with the parachute. Okay, so that we do not lose either the body tube or the nose cone. So parachute is used for slowing down the descent and reducing the ground impact of the body when it is falling from the apogee. Shock cords, that is the cord that connects all the three together, it also acts as the shock absorber, because it is already moving with high speeds, and when there is ejection of something out of it, there is vibrations and shocks that generate. So in order to minimize them, it also acts as a shock cord, or a absorber. Now when you talk about parachute, um, it can be of anything like plastic. Mostly when used for model rocketry, it is made up of plastic itself. So, and there are techniques that can be used to fold the parachute. First is the fast fold, and second is the slow fold. So as the name suggests, the fast flow, what it does, it immediately inflates the parachute. That is, the parachute doesn't take time to inflate itself after it is being ejected by the body, right? In the slow parachute fold, what happens it takes a bit of 2 or 3 seconds for the parachute to completely deploy, create that backward push, and then give that descent. So it is up to you. If you are in a rocketry competition, it will definitely matter the descent time or the descent rate. That is the time that it will take to come or land on the ground back after it reaches the apogee, or the maximum altitude will be counted. So you'll have to take care that what fold you're going to put for your parachute. So that comes when you're actually performing on ground, on site. And there are other techniques, like, which are called as referring of the parachute, which are again used to decrease or increase the drag. So I'll just tell you just a brief on that. So this orange part is called as the canopy. This white small ropes that go from canopy to this point are called as the shroud lines. And this single one that comes out is called as the shroud cord. So if you want, to reduce the drag, simply deploy it as it was. But if you want to increase the drag, what you do is you add another one rope in the middle of the parachute and connect it to the shroud cord. By doing so, what you're doing is you're stabilizing the parachute, you're increasing the drag, and that is reducing your landing time or the descent rate. So these are some techniques that you can go through. Watch multiple videos on YouTube. You have a lot of content there, so that when someone is talking, you can actually visualize those things out. So that's everything that you will be needing so far in this competition. Also, if you want to, Yash will walk you through the open rocket, but here you can get your CG, CP that is noted by red and blue dots. You can get the value of stability here, then length, diameter, mass with motor and without motor, also your maximum altitude, your velocity, and acceleration. All this data can be calculated from Open Rocket, and there are simulation graphs as well, which can be used to evaluate. So this is basic theory that you guys will need while solving the problem statement. Also, if you do not have any understanding of the forces or the laws or the physics involved, just let us know on the group and we'll share some material which will help you to. Yes, you can go
So
ahead, I guess.
yeah, okay. So we will take the all the questions the last of the session.
Hmm.
So let me present my screen. So instead of going with the different thing and make down new model rocket here, we can go for understanding the whole thing, how the procedure and all things. We'll directly go with the examples. So this is a when you open the open rocket, there is a like screen and the interface you will get. Okay. So first of all, simply you can to like avoid any mistakes and things in a physics, like we all know, like that how units are important, right? So firstly, all things it's depends on units. So you may go first of all in references. Actually, it's my screen visible, right? Completely, all dialog books and all.
Yes, it is.
Yeah. So here in a general way, like where is it will the save as a default and all things. The design, simulation and launch. So it's default uh, ground settings and all. You may change later. And units. So definitely the units. So rocket dimension, the mass, the force in which unit you will take, and it will be the understanding on how you will go with it. These, right? So like focus on these the units. So there is no mistake and in calculate the opposite and any force or anything. Okay. There is a material, so there is no need to use anything and the graphics. So you can like keep it is as it is. Problem. So there is a file. So you may go with the new like new project and new rocket model rocket and open here. And the simple we will take from the examples. There is a after okay. Let me first introduce how you will download. So simply like at the open rocket and you may go with these and open rocket simulator. So you can directly download these download version for the Windows and other operating systems. You may also download. Okay, for the Linux and Mac OS is also available. So after download, there is a make click and there is a exe file for the Windows. So it's directly you can install directly from there, and from other operating system you may install as it is. Okay. So after downloading, you have to go with this step, and now we continue for this. So we will go with this simple directly the simple rocket model which is inbuilt. So simply click on the so it's say like design the name. So like whatever you want to give the name, comments, revision history if you like change continuously, and designer name or comments and the description you can write like about what and what kind of thing and what purpose you will use. It's for you only. And after go, as Ruchira says about all these mostly component. So like we know how the nose cone. So in simple, you can see here the model rocket. It's already made, made up. So first you have to click on the nose cone. So it will open like this. So it will add only the nose cone. And when you click on here on the nose cone, double click, maybe use this edit or you can directly double click on this nose cone, okay, on a screen here. It will also open this same dialog box. And here mostly you have to add and change this in these general settings as of now. So there is general settings, as there is a lot of types. So here you will find some of the types. It's a conical, ogive, the ellipsoidal, power series, parabolic series, and hex series. Okay. So as Ruchira said, like for now an experimental purpose and the student model rocket, mostly they use the ogive shape parameters. Okay, and there is a like shape parameters. So mostly it's one. There's a mostly changes are here. The nose cone length. So it's a nose cone length is from here, the pointed this here to its here. Okay. So we'll also change. Okay. So you can see the changes here. So it's not changes from here. Okay. It's a shoulder like we connected this tube, body tube. So the length will change from this here from here. So I can fix this. In the base diameter. The base diameter is same. The diameter you will see here is the same. It will be here. And the wall thickness. So like there is a wall thickness. Yeah. Okay. Secondly. Okay. So there is a wall thickness. So wall thickness is like it's have some thickness, right? The you will use any kind of material. You can see here the materials. So it have material have some thickness and cardboard or polystyrene and other uh, materials are given here. So it has the thickness. So it's completely on the how the thickness you will use. So it's depend on the you will purchase a material or this cone from the direct to the market or make from on maybe 3D printed or something. So it's depend on that thing. Okay. Now we go with the shoulder. So this is a shoulder and we take looking here. It's about this thing. Okay, the connected to the on a shoulder part, it will connect the this body tube. Okay, so it will come on the body tube. So for this the diameter, so in this diameter is a kind of this inner thing. Okay, for the nose cone shoulder, the connecting area, it's a outer diameter, but for the body tube it's a inner diameter. Okay, so you will also understand after seeing this rocket model here. So same the length. So mostly in very practical ways, the length will be one fourth of this shoulder connected uh, area length is mostly one fourth of this nose cone length. Okay, so mostly people and the students consider as a one fourth of this nose length. Okay, so you may also consider, and then it's completely depends on you. And after you run the simulate once, and if you find something like waves to increase or decrease, you may do that. Okay, then the same thing the thickness. So it's also have a thickness. So in the inner diameter, so depends on the how inner diameter or the thickness it will be vary. Then no need to go in override or appearance or anything. So it's your uh, noise uh, nose cone how it will you will create here in a open rocket. Then after in nose cone, you have to like see it's give the name in a here, and then you have to click here and then add a body tube. So it will add completely below from this nose cone. Okay, so you may also take care of this thing if you okay, then we go ahead. So in a body tube it's a completely see it will highlight, right? So it will from here the nose cone hand to end of this rocket. Okay, so it will it's a like single stage rocket, single stage motor rocket here. So its ending is here. So here is also same thing the general, and we have to use give the body tube length here to here, and the outer diameter is most probably same with the nose cone. The which diameter you will give the nose cone, its diameter is 0.984. So same it will give you have to here 0.984, and the same is inner diameter. So it's a gap between here. Okay, so it's a simple gap between here. You can find here, right? So it's a inner diameter and the wall thickness is the same. So you may click. It's automatic. So it will directly. You have to enter this inner diameter and the wall thickness. So it will automatically calculate the outer diameter. Okay. And yeah, all the things you have to also take care of this component material and the component finish. So SM here you can find here the components, the PVC, and here is you will find most of these components is density, which is normally used. But if you have any custom component, so it depends on how you will use. So you can also go and compound this custom component, give the name, give the density in whatever uh, like unit you have to choose. Okay, then there's an option add to material to direct database or uh, for this project or this purpose only. Okay, so it's complete on you how you will use. So then it's also there's a motor, no need to go ahead and override or anything as of now. So there is a data you will fill. Then yeah, so after this you have to no need to click on this first in a rocket name. You have to click on this body tube, and then you have to attach the choose your fins from here. Okay, so if you like click here and then you will choose any fins, so it will connected on this it will not connected on this body tube. Okay, so this is what you have to take care. So after you will see even the option after that only. So there is here it's a choose the trapodizer fins. Okay, so click on that. So now there is a number of from the starting the number of fins. So you will find the some model rocket have the three fins and the most probably three or four fins. Okay, so for that you can also change, and then you will find see it's three fins, right? You may also like find from the side view, a back view for this. Let me close for now. And 3D figure. So this is a 3D figure, and then the unfinished 3D. So whatever material you apply, so it directly see it's a cardboard, it's a polystyrene or all things, right? And now it's a pack and it's a 3D finish. Okay, so it's completely pack, and how the appearance we will give, it will completely look like that. So again go with the side view. So you will find there is a uh, three fins. Okay, number of fins. Now the rotation, so it will rotate in this direction, uh, like with respect to this rocket direction axis. So there is no need to change maybe. Okay, then root code. Go with the root code. So you know the how the what is the root code. So which side it's attached to this uh, rocket, it will call the root code. And this is a root code is not, but there is a length only. So from here to here. So this is a length of this root code. The tip code, it's the opposite direction of this line. The length of this line, it's a tip code. So that, and the height. So height, you know how the like this trapezoidal geometry. Uh, Maybe if you know about that, so this is all things about that you have to fix. So depends on this height, root code, and the tip code. The all the like why we use the fins, right? For the stability purpose and the maintain the CP. Okay, so because of all the things, all the geometrical parameter you will change, though you will also find the changes in the CP. Okay, so you will also look at the CP is here in a red point, and the CG, the center of gravity here in a blue point. Okay, so height and the swept length. Okay, so swept length is nothing but like you will change the swept length and the swept angle is mostly same. Okay, so you will if okay it's a 39.8, but if I need to I want to increase the swept length, so it will tilt in this down direction. Okay, maybe in your left, but if you uh, like imagine in the standing position, so it will in the down direction. Okay, so if I increasing, it will go down. So it's a swept angle. and let me increasing to 40 and 45. So you will see it's go in a down direction. So it's a swap angle here. Okay, and the now is a position to this relative to. So there is a thing like the position. So you need to define the position. It's up and down. Okay, so now it's a zero and completely bottom relative to bottom of this parent component. So the parent component is you can find is a body tube. So bottom, so it will touch the end of this fins to the bottom of this body tube. Okay, so which is its mean. Now if you want to change to the top of the parent component and so and go with like this, put a zero here. Okay. So you will find like it will top of this parent component. Okay, so same you will now give the plus uh, 2 inches, so it will go down and more. It's the same length of this body tube. If you give the length of the body tube, okay, and minus you have to put this root code. So minus you have to root code, so it will in the same direction. Okay, like same position. So this is complete depends on you how you want to take a relative to any middle, bottom or tip of this nose cone. From here you can also set the from which distance we have to put these fins. Okay, so for now so take zero from the bottom. So this is a what the thing is fin about fins, and here the cross section. So it will the rounded. Okay. So what is about chord section? Let me go again in 3D view. So you will find the round area, the square, and the airfoil. So it's giving the fin cross section. Okay, so it's a so it will like provide in a 3D finish here. Okay, so it's a rounded or maybe it's not shown here, but it's given in a here. So it's rounded, maybe cross section filled with this square or maybe some kind of aerofoil. Okay, as of now it's a rounded. You can go inside and provide the thickness of these fins. So again, so what is the thickness of these fins? Okay, so we'll see here the thickness. So this thickness it will provide from here, and you can change and the component of material and the finish this material. So both the things are like change the in a mass here. So after adding the all the stage and components, you will find the component mass here. Okay, and after you like changes completed with the changes, you will find the total mass of this uh, motor rocket with the motors here. Okay, so we'll take care of this whatever you like give as a constraint, the mass constraints, there is no need to go more than this mass and other things. You have to take care of this. Okay, from here. So after adding all things, after calculating, or maybe you take whatever the strategies you have. So we'll take care of this. It's not go beyond this constant parameters which is given in the whatever competition. Okay, and after this, these fins, you have to go with this inner tube, and this inner tube you will find here. So there is a after go in a inner tube. So here it's a inner tube. So there is a in inner tube you have to put uh, engine lobe and other things. Okay, so in a inner tube it's a simple the body tube and another thing is inner tube for the put a motor in the solid motors in the inner tube. Okay, so there is also the same thing, the outer diameter of this inner tube. So this is a completely gap between, so it's a completely gap between this central ring outer diameter and this body and the inner diameter. Okay, so you have to give the this that margin, and the outer diameter is the same the inner diameter of center ring. Okay, we will take talk about the center ring here, and the inner diameter is the same as the motor, the whichever type of motor you will fit into this inner motor. It's the same thing is the inner diameter of this inner tube. Then there is a talk about the wall thickness, so it will automatically calculate it from here. Okay, in the length. So it's also the thing like you have to put the, you will put this length of this inner tube and the your motor, the solid motor, is the same, or maybe you can increase this inner tube length to maybe give them more stability and kind of purpose, right? So there is like also the same thing, the position. So which position and where you want to locate it this inner tube. Okay. So there is in most of the rockets for the igniting purpose and other things for the stability purpose, it's little bit some amount of this area. It's little bit out from this body tube. Okay, and it's most probably it's most important like for the ignition from the electric circuit. It's need to go outside from this body tube. Okay, that's why it's outside from the from some of inches. And here the component material as it is. Then there is no go on ahead. Okay, and about this engine block. So for the engine block you have to use, because when you fix it, you know you have the like amount of this thrust and major it will experience, right? The rocket will be experienced. So there is no like manufacturing or kind of a practical problem you will face. So that's why it's an engine block. It's also the same work. So outer diameter is here, and the inner diameter is the wall thickness length, and it's for them when it will ignite, it will like throw out some of impulses, right? And then there is also it will jerk observed by this engine block. Okay, otherwise it will like go upside and damage all things, and instead of going rocket um, upside, it will the this motor engine or inner tube only go upside. So to like prevent these causes, we have to use this engine block. And now go with the center ring. So centering ring is to like hold this inner tube with this body tube. Okay, they you can put 3 to 4, depends on like how length of this model rocket and the motors, solid motors you will use. Okay, so here they use 2 central rings, one located is here, the end of these, and most probably you will find they will use and located is end of this body tube. The second one is near to this ending of the fins. Okay, and if there is a root cord is long or kind of thing is here, and maybe about the motor length is like more than some distance, so they will also use a third centering ring to like uh, stick this inner tube to the body tube like and steadily. Okay, these all things there is, we can also like plus and down to this relevant to this uh, um, bottom skin. Again, no need to change anything, override documents. This is another center ring you will find here. So they put here the another center ring for the same thing. Now, so if you make it's a reusable rocket and it will have some you have to recovery system, you have to add some recovery system. So there is some components. Okay, so after the all things we will see in these inner component. Now again go in these components. Now we have to go in a mass objects. So this shock tube, parachute, and the loading thing, all mass components are all will be come into this mass objects. So in a recovery system, you have two things: the parachute and the shock code. Okay, so like you have to put the shock code. So there is go and adding the shock code, the name. So generally you have to define the shock code length. So and like shock code length is not so when you will see the some good videos like it's a practical, they will this talk about this shock code and how it will use here. Okay, so it's you have to define the shock code length, shock code material as I told you, and the position relevant to this where you have to put the shock code. So the black, so we'll see here kind of shock wave, so it's called a shock code. And the package length. Okay, so it's a shock code length, not the package length. You will find here it's a package length. Okay, so it's will like you will see kind of this wrapping, so it will push up this parachute to from this nose one. Okay, so it will help for that. And there is a like a shock code length, so it will provide like from what is the distance between the uh, deployed parachute and this rocket. Okay, this rocket tube, so it will the length of this, and that called the shock code length. And there is a package length, so after the folding it will go in this type of sorry cylindrical tube which have the package length of this 2.047, and the diameter is like 0.472. Okay, so you will get this idea after you may directly see in the internet there is a kind of shop code is available, ready-made shop code available, so you may directly use and catch the data from them. Okay, it's upon you. Then it's about shop code. Now and about this parachute, so there's a simple thing. So in a general case, the diameter of the parachute, so in like diameter in a sense there is no like foldable, it's a open. When will it will open there is a diameter. Okay, so it will you have to give here. And the drag coefficient, if you purchase directly from these some good companies, they will provide the drag coefficient, but in general purpose you may use this 0.80 as it is, no issue. And the shoulder line, so like as Rujira said, the what is a surround right lines, so attach with this point to this parachute, how many lines are go with this, and the length. Okay, so what is the length to this parachute, and here you have to define here. And the material of these these lines, and the you may say the road. Okay, then the relevant position of this canopy and all things, and the first injection change. So there is also like it's a open when parachute will be open, the diameter of that, and here the package length. So after the folding, so after the folding, what is the diameter, and it will of course the folding it will be cylindrical type of thing. So there is a diameter and the length. So you have to go with this. And the it's a deployed it, right. So first injection charges of this stage, so it was a single stage rocket. So after the first injection, it will the uh, with the help of the shock tube, it will be directly deployed. Okay, so there is also plus the to maintain this position of this. Okay, and the component mass and all things you will find here depends on this material, the deployment to directly calculate the approximate mass here. And now it's a loading. If you want to give some kind of weight or payload to the on your rocket model, so you will give from here. And like you have to simply click in a mass object, and you will you can easily able to give the add the payload of this 1 2 3, like it's a depends on the model rocket. So there is also same the unspecified, or you may specify some kind of tracker, the specify the payload or altitude meter, battery, some kind of recovery hardware, like uh, or some kind of specific uses. You may like use this mask type. So depends on this, you will find the changing in this option. Okay, so it will give the option. So for this unspecified, there is a mass object. So density of this total mass, the total density, and it will also like kind of cylindrical thing. So there is a length, the diameter, and the position from here. So it will, as we define the 2 gram, it will component mass is 2 gram, and here. Now it will, if you, it's a 3.15 each from the top of these parent components. So from here, but if you change this payload of 2 gram, it will also change in CG and CP. Okay, so it will just change. So you'll find the CG, CG will be changed, right? This is the thing. So you will find all things if you like change anything, and you know about this basic thing about this to maintain the stability of the rocket and control it. The most important thing is the CG is uh, ahead with this CP. Okay, so it's in a upper side of this CP, the CGs, to maintain the stability and control all things. That's why we put the fins and the payload to the upper side. So it will the CG always take in the upper side. Okay, this is about this wedding the mass component, and now it's a launch log. So you know about how the motor rocket will be launched. Okay, about there is a one road which you have to, in that road you have to give this uh, like arrange this rocket with this launch log, uh, and then it will ignite and it will go in the same direction. So provide this direction and all things, it will be useful. And there's also a thing but the length, outer diameter, inner diameter, thickness, and radial position. Okay, so radial position, it means in what position. So it will in a 90-degree. If you change, it will come in a 3. So it's not give much thing, but in the simplest way, let me go here and I will make few. You will find the lunch log is it's slightly with here is fins, one of the fins, and it will like create like this. Okay, so you is more is a position you have to set like this. If you like change, so it will go here and here. But to maintain this, there is a reason that like the road, it will passing through this launch log. It will give the stability with fins also, right? So there is something is here, so you have to set like this. Okay, and it's all about the how you configure this your rocket in a this thing. So you will find the stage one. If I will put the new stage in a here, so it will stage to stage 3, but it's completely on you how the stage you have to filling. And from here you will find the, after this simulation run, you will find other things to here. This simulation patient, and the most probably its a name is a motor, which kind of motor you will use. So let me go with this motor tube. So here there is, you will set to new configuration. So these are C6 files already here. So let
Excuse
me
me, Yash.
yeah.
I guess your screen is freezed. Nitya, are you also seeing the same screen? Or- Yeah, cool, cool. Now I got it. Fine. Continue.
Yeah, it's completely present with others, right?
Yeah.
Yeah, okay. uh, okay, so we will go with this new configuration here. There is no motor, so select a motor from here. So you will find the many brands and companies, the manufacturers have the motor, and open rocket have most of the data from these rockets. Okay, so tested data. So you will, if we purchase on some from online market, so there is some kind of data here, it will show. And if you have to go with this some specific, it's address is like locally you will available in market. So you have to like simply clear all and go with this stress. Okay, and now you can go with this total impulse. So it's like specified in this total impulse in this ABCD form. And the diameter it's also specified here. Okay, so you may directly like change to which kind of impulse from here, you can specify it here, or you may also specify it here, so you can directly get this, you can shortlist from here, or you may directly go with this from here. So if I take C5 from diameter is 0.709, the length is here, so there is a total impulse is 9. It's the single use motor, so after the single burst it will not give any other burst. Okay, so the company and the designation. So if you click here on this, and yeah, one of the select motor, so you will also show the and click on this fire motors after this show details. So it will give the details about the total impulse with the 9.1 ns, and the average thrust, the max thrust, burn time it's only one with the 1.7 second, the launch mass, the empty mass, and the uh, data points and all things. So here there is a about the description, and you will find what is the thrust curve. Okay, so in a with the time it will showing like it will first give the impulse like this, and then it will decrease, and then go with the straight in a little time. Okay, 1 point, so from here it's around 0.27 around. Okay, 0.27 to 1.7 1.665 something around. It will give the mostly linear linear thrust. Okay, then it will go decrease. So this is how curve and the depends. Okay, we'll get some high impulse motor in E. So you can see it will give the more thrust, and the rate is also in linear, not linear, in a like non-linear thing. Okay, so you will find all things here. So for as of now, we'll take CFI, and after you can check different motors, and so simply it's with the different motor you will uh, generally apply with the different simulations. Okay, so another take care things you have to see here. You have to check mark this inner tube. No, you have to see here. You didn't check this body tube, otherwise what thing is will be happen, the motor will be placed in a body tube, not in a inner tube, and we need the inner this motor in an inner tube, so you have to check mark this inner tube here. And this same thing is here, and after this you have to go in a flight simulation. So there is a some kind of flight simulation is here. So we take is a C6 5, or so you have to like create a new simulation, and it like you have to, it's a C5 3. Okay, so then you have to create new simulation. So to simulation on this C5 3. Okay, so which type of configuration of the motor we will take will provide the simulation of this. And there is also you have to change the this band and the other atmospheric and the environmental parameters depends on which kind of environmental parameter you have to the provided from this competition, or which is actually if you go and you have the actual make a physical model rocket and testing, so there is also the complete you will provided with these all the data. Okay, and there's a simulation options, so we want to go with this and simulate and plot. So we'll click here. So as of now we will go with this already simulated data, so here, and if we tick mark here, and then you have to run simulation simply here. So you will find the simulation is here, and if you find some kind of uh, thing like it will not provided some kind of errors, you will show is there data is out of date and the too short delay. Okay, so this kind of warning, there is a 3 or 5 warnings it will show if there kind of some mis compatible thing, or it will be happen, it will provide you 3 to 4 warnings. So there is also type, so you will find here. So completing after this simulation you will find this velocity of road, and the apogee, the maximum altitude, and the velocity of deployment. So at a type of deployment, what is the velocity of this motor rocket? Optimum delay, the max velocity, which max velocity it will reach, the max acceleration, okay, the time to apogee. So it's the what is the time it will taken by to reach is a apogee, and the flight time, total flight time, the ground hit velocity, it which velocity it will hit the ground and come back to the ground. So this is kind of data, and you will also check from here after clicking the plot. Okay, so it will simply double click of this here, and in this plot data we will find the it's here plot, and there is also you will change the some kind of relative things like plot of this what kind of things you will need, and the x-axis what it's the most probably the time only. Okay, so with but you will also change with respect with the altitude, vertical velocity, another total velocity, another specific thrust, and zero symbol it will given, and the y-axis with there is a three types you can also change or from here, and the unit type is here, and the left auto and all things you will play with these plots. So after clicking the plot you'll find it's a red, it will be the altitude, the vertical velocity blue one, and the green one is the vertical acceleration with respect to this time. So we'll give see the graph, and you can zoom in and zoom out from here. Okay, so if you want to specific go in this direction, you can directly square as it is, so it will give the specific data at this time step. Okay, so it these around 5.25 seconds it will have the its altitude of these 928. Okay, so this kind of data you will also find from this from this here. So this is all about uh, open rocket from this scratch to this rocket designing. So after this all things you will run simulate and thing. So you will find this C65 motor configuration. So if you apply here C65 motor configuration, so it will provide the data according to that. So motor and this solid motor have also some mass. So it will also changes the CP and CG position. I mean the CG position depends on with respect to this motor mass. Okay. So if you like if we change to this A series, so you will find the CG its position. It's go ahead in the upper side, and go again in C C65 should will go downside. Okay. So these are opposites. 1098 feet. The max velocity is here, and the Mach it's also here. By default, it set the Mach number to 0.3, in because it's not a it's a completely we can assume it's a compressible flow. There is no much flow it will, and the higher velocity it will the deploy. Okay, the max acceleration and the CG and CB and the stability criteria. So in a stability criteria, you have to focus it's upper than the one and near equal to 2.5 to 3. Okay, so you have to see about this about cal about this stability criteria. It not should in a down to and lesser than one. Okay, you should check, and the final things the length is here, the and the maximum diameter and the rocket. So this is a three parametric configuration. The this is a like after simulation you will find these parameters, and this is a like for the rocket stability purpose. Okay, so apart from this simulation, you will also see here the finished model. So we'll see here the graphics. Okay, so some kind of marketing or some kind of purpose is you will change the these graphics and appearance. So for this it's about this is nose cone, this is a body tube, this is a fins, and this is lungs, which will only show in outer side. Okay, other side it will not show from the outer side. So you may double click on this, or maybe go in a body tube, double click on body tube and appearance, or maybe you can directly click on this, double click on this body tube, so it will also open the same dialog box and go in appearance. So there will you can define the use default color for the figure style and the appearance. You can like uncheck this use default and provide you can give this texture and photo. So it will the photo it will they will use for as of now, and you will merge the shine and the other effects you can edit from here, and scale down and scale up. You can scale up and scale down and add the offset and the what is the rotation. This you may uh, check this from the simple editing options, right? The scale down, scale up, offsets, and all things to make very good and a presentable mode. So this is only about this appearance, and you may also like uh, you have if logo, if anything, your team or anything, you can also like attach here in a body too. Okay, so same thing in a fins. So because of this, they use some kind of appearance as a PNG photo. So that's why it's appears like this. Otherwise, if there is no texture, you can directly add the color. Okay. So if you change the color and click on OK, so like as of now, it's for uh, they apply the photos exact texture, so there is no appear in the color. But if you don't apply in a non, you will find there is a color of this whatever you apply here. Okay, so as from that you can change this thing. And okay, so a good quality, let me take is a red. And after that you can go in a tools. So there is after edit there is a tools as there is component analysis, rocket optimization, custom expressions, and you may use those things. And so now, but you may also use the photo studio. So there is a they inbuilt there is a provided some of the environment. So there is a pitch, your role, and the camera position of these whole things. You will change and go in environment. You may change lighting set sunlight. So what kind of color contrast you need, the sky altitude, the sky color. Okay, and there is a one thing is sky image. There is a some kind of environment it's provided. So we may change and the orbit. Okay, so image created by NASA, and there is also some kind of effects you may apply. Okay, so now you will find the smoke, little bit smoke around here. The smoke opacity you may decrease or increase the frame and the flame, and the color of the flame you may also change. If I need kind of blue, will change it to like that. The aspect ratio of this flame you may increase or decrease from here. And the sparks, so it will provide some kind of sparks change. Okay. First let me change the mountain and to the is yellow. Okay, and you will find here the sparks and the speed. So you may change, so it will go, it's a like steady effect, and it will provide the some kind of, it will go in a speed effect, right? You will find the difference here. So this is for, and you may go in size, window size, and you may take the picture. Okay, it's the save image, and you will click on this, you may save at your place. Okay, so this is all about we have time also, so 6:15, and it's completely the introduction of this open rocket from the scratch, and the some of the tools is we show here. So this is about this open rocket is introductory, and apart from this, you may find another useful things in go in this same website openrocket.info. In docs, you will find the user docs. Sorry, in a you may go in the technical docs, and you will file this open rocket technical documentation. So it's in a PDF. So after open it, you will find the some kind of data here. So how what is the use in some, this is it's right here. So you may go with this, and it's really help for the components and as a beginner. And the conical or give the nose cone types and the drakes and the most of these things you will find from here. Okay. So okay, so now it's a quick Q&A session. If you have any question regarding anything, think it's like take to the difficult, you may ask here. Okay, anyone have any question?
If you guys do not have any question right now, you can sit back, process all the information, and if you have any questions, you can ask them on the group, because tomorrow by afternoon or evening, yes.
Yeah, it's around the afternoon,
Okay.
near to 12 or 1.
Yeah. So you can take this time, utilize it, try to brush up the concepts, go through things, and by tomorrow we'll release or give you the problem statement PDF so that you guys can start working on it. Okay?
And I will also give the share this link, the open rocket documentation and all things. So it will also helpful for you. Okay. So like one thing is after launching of this problem statement, we will not give the proper solution, but we will provide the resources about the your doubts and question, right? So you it's a understandable thing. Okay, so maybe if don't you don't have any question